Okay, I want to finish these. Solve these quadratic formulas. First thing we're going to look at here is rewriting the formula down. Remember, it is x is equal to the opposite of b plus or minus b squared minus 4ac all over 2a. All right, once you have that, it's just a matter of realizing that that's a, that 12 is b, and that 9 is c. And now it's just plugging things in. So I'm going to get negative 12, opposite of b, plus or minus. Now b squared, so b squared would be 144, minus 4 times a times c all over 2a, a being 4, so that would give me 8. So now this gives me negative 12 plus or minus. Now I get, this is 36. 4 times 9 is 36. Times 4 is 144. So I get 144 minus 144 underneath, divided by 8. So this is nice. This is going to be negative 12 plus or minus square root of 0 over 8. Square root of 0 is just 0, so we get negative 12 over 8, which is, both those are going to have a 4 go into them. So it goes 3 halves. So x ends up being negative 3 halves. That's kind of a unique function there. Let's take a look at that graphically. So we had 4x squared plus 12x plus 9. Okay, so you're seeing where it is equal to 0, that's where it crosses the x-axis, and we're seeing that it's crossing there at negative 3 halves, negative 1.5 if you prefer it that way. What that tells me, because the discriminant was 0, or even if the discriminant was like a perfect square, 0 is ultimately a perfect square if you think about it. This thing would have factored using the a times c method. Even though we use quadratic formula, which quadratic formula will always work, sometimes knowing your solutions and what your solutions look like, basically if your solutions come out to having no radicals in them, it tells you that you could have approached from the onset using a different technique, maybe the a times c method, or maybe product sum technique, something like that. But that's that example. Let's go down to example 3. Now this is a situation where, if I use the product and sum method, so I'm saying product and sum is the things that multiply together give me that number and add up to give me that number. There are no such factors that multiply together give me 2, but add up to give me 2. So this has to use the quadratic formula. So again, I write that down. X is equal to the opposite of b plus or minus b squared minus 4ac all over 2a. In this case, okay, our a is going to be that 1 that's in front of the x squared. Our b is going to be that positive 2 that's in front of the x. And then our c is going to be positive 2 as well. So now plugging those things in, opposite of b would be negative 2 plus or minus b squared, which is 4, minus 4a times c all over 2a. So we get negative 2 plus or minus. Okay, now it's 4 minus, this quantity is going to be 8, so 4 minus 8 gives me negative 4 all over 2 then. Alright, so this is something that maybe you've seen before. We can't take the square root of negative numbers, but we do have a definition that says the square root of negative 1 is equal to I. We have defined that as, we'll call that the imaginary number, so we can actually rewrite it this way. Okay, square root of negative 4 I can rewrite as the square root of negative 1 times the square root of 4. Well, square root of negative 1 is just I by definition. So now we can put that over 2 as that denominator. I can still clean things up a little bit. The square root of 4 is 2. So we get negative 2 plus or minus I times 2. So we should usually write that 2I. Now divided by 2. Now because everything has a factor of 2 in it, you can basically cancel them out. It gives you negative 1 plus or minus I. Both of those are non-real solutions. When you end up with a square root of a negative, you get non-real solutions. Basically means graphically, this thing would not cross my x-axis. So let's graph what that thing would look like if we had x squared plus 2x plus 2. You're seeing that that curve does not cross the x-axis, so it never equals a 0 in the real numbers, and that's why we get these types of solutions. We mentioned in class what the discriminant tells us. I'll just kind of rehash it here in a moment. Remember, the discriminant is the b squared minus 4ac term. It's what's underneath the radical. Okay, so if that thing is positive, it means you have two real solutions, which graphically means that my parabola is going to cross the x-axis 2 times. Okay, and the quadratic formula then tells us those 2 points. If I have b squared minus 4ac is equal to 0, okay, that means you have one real solution, okay, which would look something like this, where your curve, your parabola, is just tangent to the x-axis, just touches it one time. Or if b squared minus 4ac is less than 0, so it's negative, you have two non-real solutions, okay, which means that your graph does not cross the x-axis. So it looks like the curve that we just came up with, so something like this. And it's going to have I in it when you do that. Okay. Move down to these things. Okay. So the rectangular building lot is 8 feet longer than it's wide, has an area of 2,900 square feet. Find the dimensions of the lot. All right, so this is a problem that you're always going to want to set up a picture with. Okay, just organize your thoughts. So the rectangular building is 8 feet longer than it is wide. Okay, there's two things here. There's two dimensions, length and width. And right now it's telling me more about the length than I know about the width. Okay, so my width is what I know the least information about, and the object that you know the least information about in a lot of story problems is the thing that you're going to let be your most basic variable. So I'm just going to let my width be w. Okay. Now if I want to find the length, my length is just 8 feet longer than that. So longer means I'm going to add, so we'll go w plus 8, and there's my width. Now the area of this thing is 2,900 square feet. Well, this here is a dimension of width, and that's length. If you know area,
I can't talk.
Okay, so if I'm finding area is length times width. That's our general formula. Here is my width, here's my length. So area is going to equal W times W plus 8. I apologize, my daughter doesn't understand that she can't talk during my videos. Go see what mom's doing. So area is W times W plus 8. Now that we've filled these parts in, our area we know is this number right here. So let's fill that in. Now that you have it set up this way, we got to turn this into what looks like a quadratic formula in this format: ax squared plus bx plus c equals 0. But the variable we're using is w, so it's going to probably look like a w squared plus bw plus c is equal to 0. So in order to do that, we have to distribute this w. So we get w squared plus 8w equals 2900. So now we get 0 is equal to w squared plus 8w plus 2900. Uh, Now I want to use that trick that we talked about in class. Figure out the factors of 2900 that add up to 8. So like I said, I take 2900 and I want to take the square root of it, extend it as raised into the 0.5 power. So we get 53-ish. So I'm going to go, 55. I'm going to start 2900. And I'm going to start dividing by maybe 55, see what I get. Nope, 2900 divided by 56. Nope, 2900 divided by 57. Nope. Takes a little trial and error. It's a lot easier with a handheld. Divided by 58. There you go. So 58 and 50. So right now, this thing's going to factor to W. Um, oh, I'm sorry. This would have been, I added 2900. Should have subtracted 2900. That's my apology. So we have W um, minus 50 and W plus 58. And that set of binomials should, when I multiply back out, these two multiply to give me negative 2900, last times last. And then negative 50W plus 58W should give me positive 8W. So I know I got that correct. So that tells me that W minus 50 is equal to 0, or W plus 58 is equal to 0. So I get W to be 50 or W to be negative 58. Well, W is a width, it's a length, a distance, so it can't be negative. So that answer is not what we're looking for. But now if it says W is 50, so I come back over here, that's 50. It's going to be feet. And then W plus 8, so 50 plus 8, so it gives me this to be 58 feet in length. Again, if you multiply those together, you do get 2900, and you see that this one is 8 feet longer than that one. All right, so this last one is a huge application problem that you see a lot. Um, Generally, what happens, what we're saying here, is that every object that we kick, throw, fire, shoot, propel, whatever, is going to follow some parabolic course. Okay, now there's two different situations that are occurring. We got to make sure we're talking about the right one. So I'm going to bring up an applet here that I've created to kind of explain this, but I got to find it. So give me 1 second. Okay, so what's going on here? Just trying to show you kind of the two situations that happens. Usually, the one on the left-hand side, this is much more complicated than what we're going to be doing, but this is kind of the physical application of kicking or throwing or launching some type of projectile, whether it be a ball, missile, whatever. Um, what we can do is we can create what we call a launch angle. And let me put that, I want that. Okay, so we're going to launch this thing at a 42-degree angle from the ground. Let's say that I want to, move it on top of a 10-foot building to do that. Okay, so I'm going to move that up. But once I hit this fire button, you're going to see the path of the projectile, which is this ball. A lot of times, maybe this is a ballistics type idea, and you're going to see the shape that gets traced out. Okay, so when I do that, we get that shape, which that shape is parabolic. Okay, so what we're doing here is this here is called the and obviously the x-axis, but it's in distance right now, and this is the y-axis in distance. So we see that my projectile, reached a height of about 25 to 26 feet, and the distance it traveled was about maybe 81, 82 feet. Okay, this is called the horizontal and vertical displacement of that object. Okay, now if you're in a physics class, this is a very complex problem to create the equation of that dotted line. Okay, what we're doing right now in the question that I'm asking you in uh, the examples here, where it says a bullet is fired straight up at an initial speed of 800 feet per second, it's a little bit different. This idea is if I shoot it straight up. You see this when I shot at a 42-degree angle. I want to shoot the bullet straight up. Let's launch angle, shooting straight up and down is going to be a 90-degree launch angle. And now if I just kind of, let's go reset. So from the ground, we're going to shoot this thing straight up. We got a certain velocity. It said my velocity is like 800 feet. I can't change this to 800 feet per second. It's in meters per second that we could get there. But, doesn't really matter for trying to explain what's going on. So if I fire this, you see that the ball or the bullet or whatever goes straight up, and it eventually reaches its maximum height, and then it's going to start to come back down. Okay, so if we looked at that, I'm going to change the velocity just a little bit. But if we look at that, fire it again, looking at this curve, or the path of that red ball, it doesn't show us anything parabolic anymore. That's because it went shot straight up, and it's going to reach its maximum value, and it's going to come straight back down. So there is no horizontal displacement. However, what we can do is that we can replace the x-axis with what we call the time axis. Okay, so that's what's happening over here. When we shoot this thing straight up in the air, what's going to happen over here is I'm going to plot a bunch of ordered pairs that are a time, comma, a height. Okay, so let me, just to make it a little bit better, let's make that 25, 26 and a half. Okay, so what we're seeing here, so I'm going to reset, and we're going to fire this thing, and when I fire it, we'll hit pause a couple times. So hit pause right there. So what this point here that we're seeing on the right hand side is saying is that at a time of 1.58 seconds, our ball or whatever we're shooting is at 30 meters in the air. Okay, I'll resume, and now I'll pause it. Okay, so now we're seeing right there at about 3.36 seconds, we're probably at maybe about 34 meters in the air. Resume, and we get that kind of picture. Okay, so every one of these red dots over here is a time, comma, a height. Okay, so at a particular time, we figure out how high this thing was in the air, and every object that you ever kick, throw, launch, drop, shoot, whatever, in regards to its height off the ground, um, against some time. So time being the basically the x value in an ordered pair, and the height the object is off the ground being the y value in some ordered pair. You're going to get all these points, which will always 100% of the time be parabolic. Okay, when we graph them all together. So some key ones here are, this point here when time was 0, obviously our height was 0. Here, where it looks like our time was maybe about, I don't know, 2.5, we reached our maximum. And then down here, when we get back down to the ground, it looks like a time about maybe 5.4 seconds. We get back down to the ground. Okay. So what happens is that we can create a formula for this parabola, which is actually pretty easy to do. It's going to look something for this one. Looks something like that. Okay, where this is your initial velocity. If you remember the 26.5 that I put in here, it shows up right there. Now this here is going to be a little bit different than what we do. This is in meters per second. And that's the half the acceleration due to gravity, which is 9.8 meters per second per second. It's a differential equation, so it's a much more advanced math class that actually tells you why we take half of that. But that number is always going to be half the acceleration due to gravity, which is 9.8 meters per second, or in terms of feet per second, it's going to be 32 feet per second. Both take half that, it's 16. So that's where we're going to see some of these numbers here show up when we do this problem. All right, so every time that you get a situation like this, it's called a position function, and we call it h for height at some time. Is going to be negative 16 t squared. That's always going to be the a term in your quadratic equation. But then it's plus, I'm going to say v sub 0 times t. Anything that's ever a subscript of 0, we read it sub 0, and it's basically just an initial amount. Okay, so this is an initial velocity or initial speed, and then plus h sub 0, and h sub 0 is your height, your initial height. Maybe you're going to launch us off a building, so if the building's 23 feet in the air, this would be a plus 23. But as we do this one, okay, so looking at this, we just plug in the information. This is constant all the time, okay? They'll say initial velocity. They might say an initial height. This one says we're doing it from the ground. It doesn't say anything about initial height, so that actually ends up being 0. But really, all I do is h of t is equal to negative 16 t squared plus my initial speed or initial velocity, which is 800 feet per second, and then multiply by my t. So we get that. Okay, it says when does the bullet fall back down to the ground? So that's kind of an odd question the way they phrase it, but we know the bullet starts on the ground. We shoot it straight up in the air. Okay, and if I measure against time, the height against time. Okay, so at maybe 1 second, 2 seconds, 3 seconds, 4 seconds. Try to plot what this thing looks like. It's going to be parabolic. Okay. What the question is when does it come back down to the ground? So I'm going to solve for t. Well, this is a quadratic equation. The variable is t. We can solve for that. And when it says comes back down to the ground, it's saying the h of t value, or essentially your y value, is 0. So I'm going to replace that with 0. Negative 16 t squared plus 800 t. Now you got options here. You can use quadratic formula. Okay. Our quadratic formula is always your variable equal to the opposite b plus or minus b squared minus 4ac all over 2a. I think that's a little bit more difficult than what we need right here. Because there is no constant term, what we can do is we can actually do this. We can factor out a negative 16t out of both these. Let's see what 800 divided by 16 looks like. 800 divided by 16, 50. Okay, so then this would be t minus 50. Okay, so that equals 0. So we've got two things being multiplied together give me 0. So I know either negative 16t is equal to 0 or t minus 50 is equal to 0. So divide both sides here by negative 16, I get t to be 0. So that t be 0, that's pretty trivial, but it makes sense. It's that time, it's that situation where we started, okay? And now here t is equal to 50, it's that situation right there where we get back down to the ground. So after 50 seconds, this thing comes back to ground. Well, let's see if this makes sense. Let's graph this. Just graph. Now I don't have the t variable here. I have to use x, but negative 16 x squared plus 800x. Okay, so we're seeing right there, we're going through our point 0, 0, so that makes sense. Let me adjust this. Do it this way. Just changing the view screen here for us a little bit. All right, so you're starting to see this curve looks a little bit more parabolic. Let's get the axes. Let's change it one more time. There we go. All right, so then we're seeing this thing gets to a maximum height of what, about, looks like 10,000 feet. Um, but if we scroll the way over here and see where this thing crosses back down through the x-axis, we do come out to x being 50, again being the t that we were using. Um, that's what we get to answer that question. When does the bullet fall back down the ground? It falls back down the ground at 50 seconds. Now it says, when does the bullet reach 6,400 feet? Well, instead of this being zero, instead of that being zero, we'll put 6,400. Okay, so apologize if you can hear my daughter screaming at my dog in the background. All right, so h of t is again negative 16 t squared plus 800 t. But now they're interested in when is h of t 6,400. Negative 16 t squared plus 800 t. Now in this case, I don't know. It does, kind of turn out to be a nice number here. But when everything equals 0, so negative 16 t squared plus 800 t minus 6,400 is equal to 0. Everything's going to be factorable by negative 16, so take negative 16 out. And it'll leave me t squared minus, eraser doesn't work, all right, minus 50t, and then minus, I believe that gives me 400. I'll just double check that real quick. 6,400 divided by 16. Yeah. All right, so that's nice. So now this is equal to 0. Just going through our factoring rules, we can divide everything by negative 16, so we get t squared minus 50t minus 400 is equal to 0. So now I'm looking for two numbers that multiply together to give me negative 400 and add to give me negative 50. So that's going to give me, t minus 40 and t minus 10 is equal to 0. Solve both those for 0. So we get t to be 40 and t to be 10. So those are the two times that I reach 6,400 feet. So let's see if this makes sense. Let's say that I go negative 16x squared plus 800x. And then the next part was, when does it equal 6,400? So let's put the right-hand side 6,400. And I got to do that differently. Y equals 6,400. And we get that curve. So let's see. You see it right there where those two intersect. The x value is 10. And then here where these two intersect, the x value is 40. So it's going to reach a height of 6,400 on its way up to its maximum. And it's going to reach, obviously when it's coming back down, it's going to reach that same height of 6,400. So that's, kind of the physical nature of what's going on behind the scenes. Now we factored this using practice sum techniques. We just take GCF out of there. But if you want to use quadratic formula will work all the time. Whether you want to start with that or use that as kind of a backup at the end to double check, whatever, it will always work. Okay, these are additional examples. Strongly suggest that you guys go ahead and work through those. Maybe the next day or so I'll put together another video of those 4 groupings there. Do about maybe 2 from each section there and post that for you.